We will now proceed with part 4 of our lecture, where we would be discussing experimental designs for optimization. We will be discussing about response surface methodology or RSM, common experimental designs for RSM, and continue our sample problem earlier. Curvature is best explained by higher order model terms, the quadratic terms. In our case, a squared, b squared, and z squared. However, factorial designs are not enough and will no longer provide sufficient information to adequately model the true surface. The a squared, b squared, and z squared model terms are confounded on the curvature term that is detected earlier by characterization. What we would do to isolate these quadratic terms is to add several runs to the design and implement an RSM experiment. Response surface methodology or RSM uses a quadratic model to describe the response surface. Since more runs are required to de-alias pure curvature, it can estimate linear, interaction and also quadratic effects. So, the new experiment involves adding a number of unique factor combinations. These are some of the desirable properties of RSM designs. They can detect lack of fit or LOF, internally estimate errors by replicating some runs, check for constant variance, incorporate transformations if required, and is suitable for blocking. Lastly and most importantly, with a minimum number of treatment combinations, you can get a lot of insights from your data. Two of the most commonly used RSM designs are the Central Composite Design or CCD, which can either be a regular CCD or a face-centered design or FCD. Second is the Box-Benken design or BBD. Others are the split-plot central composite design, mixture design, three-level factorial design, hybrid design, pentagonal design, hexagonal design, and optimal designs, which can also be accommodated by this software. For this lecture, however, we would be focusing our discussions only on CCD and BBD. The first type of CCD is the regular CCD or RCCD, which is made up of two components. The first component is the two-level factorial or fractional factorial design with center points, while the second component is the additional group of axial or star points extending outside the factorial box, as shown graphically later in the figure. These star points are added to de-alias pure curvature. For a regular CCD, we now have 5 levels for our design. These are the low axial or minus alpha, low factorial or -1, center or 0, high factorial or +1, and high axial or plus alpha. This is the design for a regular CCD for 2 factors. As you can see, the factorial box was just added with axial or star points protruding outside the box. For the experimenter's convenience, the alpha values are calculated by the software. For rotatable CCDs, alpha is equal to the 4th root of 2 raised to k, where k is the number of factors. Similarly, for a regular CCD with 3 factors, we just have a factorial cube with star points protruding outside the cube. Aside from the regular CCD, another commonly used CCD is the face-centered design or FCD. Like regular CCD, FCD is composed of two-level factorial or fractional factorial design with center points and a set of axial or star points. However, these axial points are positioned on the center of the faces of each factorial box. Unlike a regular CCD, you can see that the additional star points are just on the edges of the box or on the faces of the cube. These points do not protrude outside the factorial box. Also, the alpha value for an FCD is equal to 1. And lastly, unlike a regular CCD, only 3 levels of a factor are included in the design. These levels are the lower minus level, center or 0, and higher plus level. When do we use FCDs? First, you may use it when regular CCD star points may break the envelope of what's safe for your process, as dictated by either experiment or equipment limitations. They can also be used when star point values are physically impossible. Example, for length, sometimes the regular CCD star values tend to be negative, so you cannot use a regular CCD. And lastly, it can also be used if you include a factor, such as a dimension or a percent, and the lower star point comes out negative. We can point out based on the earlier discussions that the general elements of CCDs are the two-level full or fractional factorial design, which aids in the estimation of first-order and two-factor interactions, center points which estimate pure errors and tie blocks together, and the added axial or star points, which are used to estimate pure quadratic effects. Let us take a look at the design matrix for a 3-factor CCD. This design has 8 factorial runs, 6 axial runs, and added center points. In this particular matrix, 6 center points were added. If this design will be performed and divided into 2 blocks, these center points must be distributed between the blocks. The Box-Behnken design or BBD, on the other hand, is recommended for designs involving 2 levels for at least 3 factors. It is a combination of a 2-level factorial design with incomplete block designs or IBD, and then adding a specified number of replicated points. And more importantly, we must remember that BBD cannot be used to augment a factorial design. The design matrix is obtained by substituting the 2-level factorial design on the left and incorporating it with the IBD on the right. Similarly, the Design Expert 11 software will do it for you and generate the BBD experimental runs. At least 3 center points are required for Box-Behnken designs. This is the structure of BBD, and again, the center point must be replicated at least 3 times for the design to be adequate. Before we continue our sample problem, after the analysis of data and model generation, response surface graphs are also generated by the software to visually describe the effect of the factors you considered on the response. Usually, graphs may either be simple maximum, a saddle, or a rising ridge, as shown in the figures. However, it is also possible to obtain graphs that deviate from these common types.